welcome back. We're going to be doing more work with parabolas today, which is Unit 8, Lesson 2. So the graphs of quadratic functions are more complex than linear and exponential because they include a turning point. That's either the location minimum or the maximum, as we discussed yesterday. So today we're going to explore these functions more, and to do that we're using our calculators. But first we have to examine one additional quadratic function by hand. So we're going to start out with looking at y equals negative x squared. So for part A, they want us to write this parabola in this form. So what they mean is, instead of having just a negative, actually write a number for A. So instead of y equals negative x squared, I'm going to write y equals negative 1x squared. And then we're going to fill out the table below. So we're doing this one by hand, and then the rest of what we're doing in this lesson is basically all going to be on the calculator. So all we're doing is we are finding the y when we are squaring this and getting our negative answer. So this is negative 1 times negative 3 squared. So this is 9 times negative 1, so that's, negative 9. So negative 3, negative 9. And I hope that you can see now why they had us write this negative 1 out here, because leaving the negative here is too easy to accidentally include that in the parentheses, so you can see that it's not being squared. So this would be negative 1 times negative 2 squared. So this is 4 times negative 1, which is negative 4. And this is negative 2, negative 4. Y equals negative 1 times negative 1 squared. This is going to be negative 1, so this point is negative 1, negative 1. Going on, negative 1 times 0 squared, that's 0. So this point is 0, 0. When we plug in 1, negative 1 times 1 squared, we're going to just be getting the same answers. 1 times negative 1 is negative 1, so this point is 1, negative 1. When we plug in 2, same thing. This is 4 times negative 1, so that's negative 4. So this would be 2 comma negative 4. And finally, we have negative 1 times 3 squared, which gives us negative 9. So as you can see, we still have our y values repeating after a certain point, which we already learned yesterday would be our turning point or our vertex, right? And we're seeing that they're repeating, they're mirror images of each other. So you can also tell, like we did yesterday, whether it's a maximum or a minimum by seeing if the numbers are approaching the turning point, getting larger or getting smaller. So you can see that as the numbers are approaching the turning point, they're getting larger. So this is going to be a max. So this graph is going to be upside down. So basically what we're going to do is we're going to look at our points here. This is 0, 0, 1, 2, 3, 4, 5, negative 1, negative 2, negative 3, negative 4, negative 5, and this is all the negatives. And careful, because you can see this is the x-axis, so that's why this is all negatives. They've just zoomed in on a part of the graph that will most accurately show what we're looking at here, okay? So negative 3, negative 9 is here. Negative 2, negative 4, negative 1, 0, 0, and then we're going to be mirroring that on the other side. 1, negative 1, 2, negative 4, 3, negative 9. So as you can see, we still have that same shape of the parabola, but it's upside down. Okay, so we're going to state our range. Remember our range going from bottom to top. So we're starting at negative infinity because it's going on forever. That needs to have a parentheses. And we are ending right here, which is 0. And that's included. So there's a certain term that we use to describe when a parabola is facing up or facing down. And that word is concave up and concave down. Okay, so concave means that it opens upward, so that looks like this. And concave down opens downward, and that looks like this. Okay? So basically, what we're going to do is we're going to see what it is about the equation that determines whether the parabola is going to be concave up or concave down. So we're going to look at these in our graphing calculator, and we're going to see if we can figure out what that is. So notice it's telling us to use a standard window. So when you go in your calculator, you want to make sure that your window is set standard, which means -10 and 10 for all of those values. So before we start, let's go to window. So mine is not, okay? Now if I get out of here and do zoom standard, which is 0, it'll automatically set, nope, that was, I'm sorry, zoom fit, excuse me. Zoom standard is 6, zoom 6. Zoom 0 is zoom fit, I'm so sorry. Okay, now it's gonna automatically set my window back to that standard. Okay, you could also do it by hand, but if you do zoom 6, it'll bring you back to your standard. So let's go into y equals, and we're going to put this function in 3x squared plus 6x minus 4 and see what we get. So 3x squared plus 6x minus 4. Okay, and we're going to take a look at what we see, and we're going to sketch that. Okay, so this is a concave up parabola. It's beginning somewhere, I'm sorry, it has a min, and it's somewhere around here. So when we sketch this little guy, it's gonna look something like that, more or less. All right. Now we're gonna go in and we're going to clear this out, and we're gonna do the next one. This one is -x squared plus 6x plus 1. So carefully using the negative instead of the subtraction. -x squared plus 6x plus 1. Graph. And this time our graph is concave down. So it has a max. Looks very similar to this graph, except it's going basically through the origin like that. Okay. And finally, we'll do the last one, so clear that out, and you're gonna enter in -2x squared minus 8x minus 4. -2x squared minus 8x minus 4. Remember to be careful with using your subtraction sign versus the negative sign. And again, we have a concave down graph that has a maximum point. So that's somewhere around here, like that. Okay. So hopefully you're noticing the pattern here, that if the leading coefficient is positive, it's a concave up, meaning that it points upwards, it opens upwards. And if your leading coefficient is negative, and up here too, negative, then it is concave down, which means it points downwards. In other words, it's upside down. Okay? So one way that I've had success teaching this in the past is positive is a smiley face. Yay, I'm happy. And negative is a frowny face. I'm very angry and sad and mad. Okay? So let's move on. We're going to explore the reason for this pattern more in the next exercise with much simpler quadratic functions, okay? So we're going to go ahead and use the calculator to sketch a graph of each of these using the indicated window. So what I'm going to do is I'm going to have you guys pause, and you're going to sketch these yourself, then unpause and take a look and see if you did them, you know, accurately, etc. And then we'll move on to the last exercise. But one thing just to note before you begin, make sure you're using the window that they give you. So this is a standard window, this is a standard window, this is a standard window. They're all standard. All right, never mind. Okay, so we're just going to make sure we're on a standard window when we graph these, okay? So go ahead and pause the video and sketch all 6 of these, and then we'll unpause and compare. Okay guys, so here are my graphs, and hopefully your graphs look the same. You'll notice when you begin with 2x squared, you have a slightly wider, normal looking parabola, smiley face one, because this is positive. Then when we go to 3x squared, it's a little bit skinnier, but it's still a smiley face. The 3 is positive. And for C, it's even a little bit skinnier, and it's still smiley face because it's positive. Down here, you'll notice that the graphs are the same width in terms of, you know, squeezing together or being further apart, but they're just flipped over upside down, and that's because each of the coefficients are the same, but they're negative. And that's why we have the frowny face for each of these. And again, you notice that the negative 2x is a little bit fatter, so to speak. The negative 3x is slightly skinnier, and the negative 4x is slightly skinnier. That is another pattern. I think it's going to be discussed in the next lesson. I have to double check on that. But the smaller the coefficient is, the wider the parabola is. The larger that coefficient is, the skinnier the parabola is. So, in other words, if I had a graph that said, function that said 1/2 x squared, this would be even wider. And if I had one that was 10x squared, it would be even skinnier than this. Okay, that's just another pattern that we can see. So let's see if we can wrap this up by filling out these blanks here. We can determine what controls the direction that the parabola opens. So we already summed it up. But the parabola will open upwards or be concave up. In other words, it will look like a smiley face if a is positive, right? So we'll write that like this: a is greater than 0. Okay, and I'm gonna just write smiley face for positive. Okay, it's the easiest way to remember. I know it seems pretty juvenile, but it just makes the most sense. When you have concave up or a positive a value, you're going to have a minimum here, right? Think about it. It's your lowest point. Your parabola is going to open downwards or look like a frowny face if a is less than 0 or negative, right? So you're going to have the frowny face when it's negative. And of course, we're talking about a, so we're only talking about the leading coefficient. That's it. Okay, guys, that's actually it for today's lesson. I've been assigning basically just the fluency for homework, so I just want to say to please feel free to try out the applications or reasoning problems. Some of them are not really that bad. I'm just trying not to give you guys too much work. So if you'd like to try them out, go ahead and enjoy.